Hi, so specifically, this is about trading in Python 3, because while our platform was still in Python 2, before we converted it to 3, we were just losing money all the time. But once we switched to Python 3, we became really profitable. It's unfortunately, that was just a joke. We started out in Python 3 from the very beginning, and we really love it, and we see no reason to work in Python 2. Anyway, my name is Víťa. I'm a software engineer. I really like to work on hard problems, preferably involving mathematics, which is exactly what I do at Quantlane. That's who I am here to represent today. At Quantlane, we develop and operate our own trading platform and also strategies that run on that platform. So in other words, we trade stocks, and some of the trading is being done manually, and all the trading is mediated by Python software. We are a small team, and we're trying to run this as a lean startup, even though we're actually part of an investment bank. And of course, all our code is in modern Python. We're currently in the process of migrating to Python 3.6.1. And we also have all these popular technologies in our stack that you may know. We've been doing this for about 3 years now, and I dare to say we're quite successful. It's working. Was that a question? All right.
What do you use TensorFlow for?
TensorFlow. For training convolutional neural networks.
The time series of
Yes. Maybe we'll go into detail. What was that for? I'll tell you a little bit about what it is that we're building, what our challenge is. A trading platform, in a very abstract sense, is a stream processor where we receive real-time data from market data providers. We analyze that, we make decisions to buy or sell, and then we send orders to that effect to a stock exchange. Zooming in a little bit, the platform itself can be decomposed into a couple of modules. So when we receive market data from a provider, we need to parse it from their proprietary format, work around their bugs, and each data provider has their own bugs. Then we construct a model of the market. This is in the MVC sense, so this is a representation of how we see the market. That then gets displayed in the user interface to human traders, or it is used by trading strategies to make decisions automatically. And both these parts, humans and machines, then make decisions to buy or sell, which are executed by the executor, which sends them to a stock exchange. And of course, in real life, we've got many data providers and many stock exchanges, and we want to trade in several of them simultaneously. Some of our trading strategies actually depend on that. So this talk is a story of 3 chapters: how we built this, what decisions we made along the way, and perhaps more interestingly, what mistakes we made along the way, and things that you might learn from in your own projects. So this is not a talk about trading. I think all of these lessons learned can be applied in other projects as well. So the very first chapter started 3 years ago when we just had a small prototype application that was capable of trading. So from the very beginning, we used async.io, which is a part of standard library in Python since 3.4, I believe. And back then, we only had one data provider and traded in a single stock exchange. So this was a pretty simple setup in the beginning, which is why we got away with most of the components in the diagram I showed you earlier, just pulling each other. So trading strategies would be asking every 500 milliseconds or every second, hey, is there something new? Hey, is there something new to do? And this is obviously not an optimal design, but in the beginning, the data volume was so low that it allowed us to get started quickly. But even back then, we had a couple of components that were decoupled, and they talked to each other through queues, and they didn't necessarily have to know too much about each other. And this, we think, was a good start, a good decision. A quick example how that might work in async I/O. You represent your component by a class which implements a very simple interface. There is the start method, which you call from the outside when you want to activate that component. And this component might be a parser, maybe, or a model, or a strategy. So you just set some sort of a Boolean flag, and then you tell async I/O to start the underscore run method in the background, so to speak. What that does is async I/O is able to execute this coroutine, notice the async keyword, and it will spin in a loop, and in each iteration, notice the await keyword here, it will wait for data to arrive through a queue. That queue is an object provided by async I/O. And the framework allows you to have many await statements waiting for data at the same time. So async I/O, when it reaches this line, it will check if there's any data in the queue. And if there isn't, it will suspend that coroutine, that method, and it will be executing something else in the meantime. So this is very powerful. And then maybe at some point you want to stop your component, so you just clear that flag that allowed the internal loop to run, and you cancel the current iteration. For those of you taking photos of the slides, I'm planning to put them up on GitHub sometime next week, so you'll get all the code. Now, a less than stellar idea that we had was to use Pickle to persist state of the trading platform. So all the components in the platform have some sort of state. For instance, trading strategies remember their configuration that was set by the users at runtime. Or we remember all the orders we send into the market. So we did this originally by having a huge dictionary with namespaces. Each namespace represented a component in the system. And then when we wanted to save that, we used Pickle to serialize this huge dictionary and write it to a file. This was an absolutely terrible idea, and please don't do that. One problem was Pickle itself. Many of you probably know that Pickle is a terrible thing that's very alluring, very seductive, because it's easy to use in the beginning, but you run into problems once you start changing your code and having the previous versions serialized on disk. And another reason why this was bad was that the single dictionary grew quite a lot over time, and serializing this and writing it to a file became a stop-the-world operation for the platform. And obviously, we want to do this as often as possible so that we don't lose state in case of crashes. Something that wasn't such a bad decision was to give this platform a web-based user interface. We used React for that back when it was a very new library, not nearly as popular as today. And the client is quite interesting in that it contains absolutely no business logic. It only displays platform state sent to it by the server, and user actions are translated into remote procedure calls on the server again. So server state is represented as what we call collections. This was inspired by Meteor.js, which used to be a very popular JavaScript framework for real-time apps. A collection is a list of dictionaries of basically any kind of objects. And every time something changed in the server process, we would serialize that respective collection to JSON and ship it through WebSockets to the client so it could re-render the interface. This kind of worked. The problem with that was it was inefficient because we would serialize a lot of data quite a lot. So we came up with some optimizations like incremental updates. So instead of sending the new collection after every change, we would just send the actual inserts or updates or deletes that were performed. And we did some batching or debouncing, so we wouldn't send data every 50 milliseconds, but maybe every couple hundred milliseconds, because humans cannot see the difference anyway. This is a recommendation. We found this library quite early in development, and thank God for that. This is an open source library that lets you open an interactive Python shell in your running process. So we added this to our server instances, and we were able to connect to live trading platforms and execute Python in them in the context of the running application. And thanks to async.io, we were not actually affecting the execution of the platform. So trading was going on as usual, but us developers could reach into the platform and maybe fix an incorrectly updated internal state, or maybe debug what was going on by actually looking at the data structures in memory. So check this out. It's really great, and it's on GitHub. That concludes the first chapter for me. Let's get to where we went next. Does anybody know where this picture comes from? Yes, the Space Odyssey. Very good. So, as we proved that our business model was working and this style of trading was actually profitable, we had to grow a lot. We grew by adding many more data providers and trading in many more stock exchanges. And we did that by blowing up the original async.io application, just adding more and more components and features to it. We ended up with hundreds of components running in the single process, which was quite impressive for async.io. On the other hand, it was problematic because async.io at its core is cooperative multitasking. So all your hundreds of components really have to play nicely with each other so that you don't start blocking your single main thread and having performance problems. And of course, that's easy to happen when you have so many balls flying in the air, so many components executing. And at this point, you really need to look into how async.io works and invest in tooling, in debugging tools, in monitoring, to get a better insight into what your application is doing. To that end, we developed a little library called IO-debug. IO stands for async.io, and we've open sourced that, so you can check it out. It provides a couple of features that help us monitor the process and find out what's running too slowly. And at this stage, we started moving to a proper event-driven design, so much less polling and much more event-drivenness, I suppose, would be the word. And to that end, we implemented a proper publish-subscribe system within the async.io process. So the way this works is you create a hub. A hub is an object that routes messages between your components in the single process. Then you create subscribers that can say they're interested in particular types of data, like namespaces, and these subscribers are connected to the hub. And then you create publishers that may produce this type of data. And the data is sent to the hub again. And then the hub makes sure that messages that were subscribed to are actually delivered to the consumers or subscribers that are interested in them. And this is a very flexible pattern. You can create one-to-many or many-to-many relationships. And publishers and subscribers don't need to know about each other. So now when we add a new trading strategy, it can reuse existing data being published in the process. And we don't even need to touch the producers of the data. Do you think this was a good idea? We think it was a good idea, which is why we open sourced it, so you can check it out on GitHub. By the way, how many of you have seen my talk at PyCon CZ last year? Quite a few. You may have noticed by now that this is a different talk, so I won't be repeating myself too much, but I just wanted to point out the libraries I spoke about last year as well. I'm quite proud of them. Another thing we improved in our second chapter was the persistence problem. So instead of writing data to disk, we started writing it to Redis, which is a data structure server. By default, it is only in memory, but you can configure persistence and replication to followers. We still stuck with Pickle because it was so hard to get rid of it. But at least we started using data structures in Redis. So Redis has lists and hashes, which are like dictionaries in Python, and sets, and sorted sets, and so on. So instead of always serializing an entire dictionary or a list of objects, we would only write to Redis what actually changed. So the writes would become really, really tiny instead of massive chunks of data. An example of how this might work, you create something like a list. It behaves very much like a list in Python, but every time you write to it, it actually forwards that write to Redis. Every time you read from it, you read data from Python memory. So there's no performance penalty on reading. And there's also no performance penalty on writing because the writes are done in a worker thread asynchronously. And, oh, sorry, you can't see the slides. And where was I? And we can batch them together or debounce them, meaning if we write to the same list index in very quick succession, for instance, we only send the last write to Redis. And this is configurable, so we may say the debouncing window is 50 milliseconds or 100 milliseconds. And that, in effect, defines the maximum period of time that we can lose data for if our process crashes. And now we arrive in the present day. This is the chapter that is still being written, where we convert the huge monolith that is very capable but has many problems into a distributed system that is even more capable and has slightly fewer problems. So what we have today is a distributed trading platform, meaning we have about 20 instances of various services, various projects carrying out the trading. And these instances might be what was originally the platform, which connects to market data providers and stock exchanges, or it might be strategies that consume data and then trade themselves, or it might be a neural network classifier that consumes data and then produces predictions about what the market is going to do next. To distribute data in this system, we mostly use Apache Kafka, at least for components that are not super latency sensitive. Apache Kafka is a message broker, and I'll talk about it in the next slide in greater detail. And for those cases when the components of the system need to talk to each other and they need to issue imperative commands, they need an immediate response to their request, we developed our own RPC framework, or remote procedure call framework, and I'll speak about that in another slide too. And another big change for us was we stopped using JSON and YAML and other human-readable formats, and we started encoding all our data in binary formats. This is because they take up less space in network traffic and on disk, and also because encoding and decoding these messages is faster. This is a challenging stage for us because up until now we only had one huge process and the failure scenarios we could imagine were fairly contained. But suddenly, when you start trading across many systems, there are so many new problems you can have, especially when you're latency sensitive, as we are, because our trades, our reactions to what's happening in the market should be in the tens of milliseconds. So distributed systems can fail in many new ways that were not possible before. You can have all kinds of network problems, or processes might die that you rely on. So this is a natural evolution for us, but we are very happy that we didn't start out this way. One of the reasons why this isn't so easy is Apache Kafka, but it's also a great tool. We just have to learn how to use it well. So Kafka is something of an extension to our publish-subscribe model, but this time we decouple producers of data, which are independent processes, from consumers of data which run in other processes. And this really very nicely maps to what we have within a single process with that library of ours. For the payloads that we actually send and receive from Kafka, we use fixed schemata. That means every type of message we send there has a strict list of fields and data types that are permissible to be encoded. So this way, we can never send a message that has an undocumented format, because that would mean we have invented a schema on the spot, which is not possible. But so that we don't lock ourselves out from future changes, we have versioning and migrations for these schemata. So if we need to add a new field or maybe change a data type of a field, we release a new version of the schema and write migrations that convert old messages to new messages. And for the actual encoding format, we use Apache Avro. That is an open source standard for binary encoding. Some of you may know protocol buffers by Google. That is a very popular format. So Avro is something like that. We think it's a little bit better. A couple of tips. There is an official Avro library in Python. It's full of features and quite slow for that reason. But there is an alternative implementation that doesn't do so much, but it's like an order of magnitude faster, which was huge for us. And to communicate with Kafka, we use IO Kafka. It's the only library I know of that supports Kafka and is based on async IO. So it doesn't block your thread when it does IO operations. It's still under heavy development, so you run into issues occasionally, but we've been using it for many months, and it's working quite well for us. Custom RPC system that we developed. You may ask why we developed our own RPC when there are frameworks out there like gRPC. The reason is we wanted support for async IO and HTTP and Avro at the same time, and we couldn't find one. And we found out that writing our own was actually quite simple. So Avro is a format for encoding records, messages, but it also has a part that describes RPC protocols. So we simply use that specification instead of inventing our own protocol. And what we're working on right now is automatic server discovery, so our RPC clients will not have to be configured for the actual host names and ports where the servers are running. And I believe this is the last interesting takeaway in this chapter. We improved the protocol that we use to send data to the user interface from the server. We realized that not everything we want to display in the client is a list of dictionaries, a collection. So we expanded this and added new data structures. So instead of just lists, we have also dictionaries or hash maps and records. This was inspired by Redis, of course, which I spoke about earlier. And we support element-level updates of these data structures. So when you write to a single element in a list, we just send that little write to the front end. We kind of had that in the earlier protocol as well, but we improved on this quite a lot in this iteration. And again, we use Avro to serialize this, so we're no longer serializing our UI updates to JSON. We use Avro. And what is nice is that it is faster to decode in the browser than decoding JSON. And that includes Chrome, which is highly optimized for decoding JSON. And this is simply because Avro is a schema format, so you always know exactly what shape your data is going to be in. I've got a toy example of how this protocol works. So imagine you have a traits object. So that would be something like a list in Python. But this is a magical list, because every time you write to it, it remembers that single write, And it can give you some metadata on what writes have been performed recently since the last flush. So here we see we're writing to something with a schema ID of 1, 2, 3. That would mean in our protocol implementation that this is a list of traits. And the payload of that write is, it kind of looks like recording a Python operation on a list. It tells us that we wrote to indexes 3 to 5. The last index is not included, as usual in Python. And the new items that we wrote to those indices are there. And when we encode this with our Avro encoder, we get a very compact message that looks like this. The first 2 bytes encode the schema ID, so that's 1, 2, 3 in this case. The following 2 bytes encode the length of the payload that's following after this. So this would be 20 bytes. And then the actual message, so that's the items from the payload and the start and stop. So I think this is pretty nice. It's just 20 bytes. But what we have there is an array of arbitrary length. So if we wrote not just 2 indices, but 20, we would still be able to encode this with Avro. And we've got other optimizations there. So we can batch a couple of these messages together and send a single binary blob instead of sending many tiny messages through the WebSockets. And we can also compact the writes. So that means, imagine you write to an index 4, and then you delete that index 10 milliseconds later. So we don't have to send that write and then the deletion to the client. We can just cancel them out. And there's quite a few ways you can cancel out operations or combine them together. So there's much less work to be done on the client and much less data to be sent to the client. So I think that has been a lot of information in a very short period of time. So just to wrap up quickly, I've got a quick summary of what I've been going through today. First one, I believe I keep saying this to everybody and in every talk I have. Async.io is great, really great, especially if you want to have a lot of independent components running in a single process. The flip side of that is if you really start decoupling your code a lot, complexity goes way, way up. So you need to invest in some tooling to debug and monitor this. So we did, and you can find some of our code on GitHub, IO-debug. The third takeaway is fairly simple. Don't use Pickle. It's very easy to start using Pickle. It's very hard to stop, because once you buy into it, migrating your persisted data becomes quite a lot of pain. So I have to admit we are still using Pickle, but we can't wait to get rid of it. Publish, subscribe, really good idea. You can do it within a single process or across many processes. And I didn't mention that we actually have adapters. So what we can do is publish data through IO-PubSub within a single process, and then there's an adapter that also sends that same data through Kafka. So we kind of seamlessly integrate in-process PubSub with publish, subscribe across processes and machines. When you start using distributed systems, be very careful about it, because there's a lot to learn. A lot to learn how to use them properly and how to operate them, how to fix operational problems you will run into inevitably, losing data or having duplicate data sent to clients and so on. We're still learning, and we're very happy that we didn't just dive into Kafka with all our data at once. Using fixed schemata for sending messages between processes is a good idea, because your code, what is running in production, can never diverge from your documentation. But you need to give yourself some sort of evolution capabilities so that you are you're able to change your messages as you grow your company and your infrastructure. And I think I didn't mention that Avro actually has some capabilities for this built in. So it has some sane behavior, what to do if it encounters a message that does not really conform to the schema it was given. Binary formats might be counterintuitive because they're not human readable. They are a little bit difficult to work with, but they save so much bandwidth and they are faster to encode and decode. And finally, sometimes it makes sense to invent your protocols that are hyper-adjusted to your use case because you can optimize a lot. That is it for me. If any of this sounded interesting at all and you would like to work on problems like these, we are obviously hiring. So you can talk to me or my colleagues around here. You can tell who we are by these little black and orange badges. Thank you very much for your attention, and I'm happy to take questions now.
Thank you. Thank you for a great talk. We have several questions in Slido. Some of them are upvoted. Wow, cool. So the first one, could you elaborate a bit why Avro is better than protocol buffers?
Yes, so first of all, the libraries for using protocol buffers are written by Google, which means they are, to this day, as far as I know, they are not compatible with Python 3 because Google doesn't care about Python 3 very much. They are really, really slow in my experience. And then the format itself, Avro, I think, is slightly better designed, so it handles schema evolutions better, and it is more compact. So the same message encoded in protocol buffers and Avro will be smaller in Avro.
Okay, thank you. Are there any obstacles of using this platform with mobile native app?
We never thought about that because we are the only users of our own platform. We've got our own trading team. Each trader has a really powerful Linux machine to trade on. It has a, I think, mid-range GPU in it, and it has 4K screens, so they can see dozens of stocks at once. We really do not need to optimize for small screens. That doesn't make sense in our case. But I believe you could run the web client on a mobile device. We've never tried, but it would probably work. On mobile Chrome, that is.
Okay, thank you. Why async.io? Why not Tornado?
Because async.io is newer. It was designed later, so I believe it learned some lessons from the previous frameworks. And it is part of the standard library in Python 3. So we believe that is the future. Either async.io or its competitors like Curio. But async.io is in the standard library, so I would bet on that.
Okay. You mentioned that you dropped the JSON. What kind of binary encrypting, decrypting code, e.g. Hamming, are you using? Don't you worry about corrupting the data?
So, who asked this question? Did you actually mean encrypting and decrypting, or encoding and decoding?
Encoding, decoding.
Okay, I see. Well, we use Avro, so that takes care of this for us. You just give Avro a dictionary of stuff that conforms to the schema that it was set up with, and it will just go through your dictionary, and it knows the order of the fields it's supposed to put in the binary message. So it knows that the first field is called start, and it is an integer. So it will encode it as a run length integer.
Okay, I saw that you developed the encoding algorithm by yourself.
Yeah, I think that would be a bad idea. We invent some things ourselves, but we pick our own battles, and we couldn't come up with anything better than Avro. I'm sure we couldn't.
Okay, thank you. Another question. Did you consider using Google platform with PubSub or AWS with SQS?
We didn't because we run on our own hardware. It is necessary. We need low latencies. We need to be close to the stock exchanges. So at the moment, we can still afford to run on virtual machines on a what is it? I forgot the name of. I think it's VMware that's doing the virtualization. but I think it's a matter of 1 to 2 years when we will have to switch to physical hardware. Even now, we're having problems with virtualized machines, so we never really considered running in the cloud.
Okay, thank you. So we have time for both questions. Maybe if you have some more, just ask away. We will see if we'll get to that. Did you try Refis pops up, Rabbit? What, Refis? I'm sorry.
Redis, probably.
Refis. Okay. Maybe just read it.
Did you try Redis PubSub, RabbitMQ, and others? We actually did use Redis PubSub for quite a long time. It was very easy to get started with because we already did have Redis. I think we decided to move to a more feature-complete system than Redis because PubSub in Redis kind of feels like an accident or an afterthought. It has some strange features like, I'm not sure if you know, but in Redis you can have multiple databases. And so those act like namespaces for the data you write in, and that works fine. But PubSub is global to the entire Redis server, which is very strange. And I think it's a consequence of PubSub in Redis not really being a core feature. And as for RabbitMQ, we haven't tried it. I haven't tried it in person. Some of my colleagues did, and I heard unpleasant stories about it, like messages getting lost sometimes if you didn't really know what you were doing. And we felt that Kafka was pretty much exactly designed for what we needed. Okay, good.
This is the old one. So thank you. Have you had any performance issues with Python so far?
Yes, of course. Most of the performance issues were due to a poor choice of algorithm and not poor choice of language, as it usually is. But of course, we're already running into some ceilings, hard ceilings in Python on performance, which is why we started converting some of our core code to C++ or Python at least. A little plug here. A colleague of mine is having a talk about Python in the main room right after this. So you might see some practical experience with converting code from Python to Python. And I expect in the following years we will only be expanding our C++ code base.
Okay, good. Why do you use convents for time series prediction rather than e.g. RNNs?
Recurrent neural networks. Yes, that is a very strange choice. It was an experiment.
But does it really work, or I just don't get it? It's a time series prediction, right?
Yeah.
And you use convents.
Yeah. I can't tell you.
Okay, thank you. Why do you use Redis configured to be persistent even though Redis is not designed for persistence, but for fast in-memory operations? What about Couchbase?
I'm not sure. I'm quite comfortable with Redis being persistent. We have it configured to use the append-only file, and we have it replicated, so there's a couple of instances persisting data to disk. So the data structures are really nice, and we've never had problems with persistence. I'm not familiar with CouchDB, so I can't compare, unfortunately. But whoever asks this question, I will be happy to learn more about CouchDB after this session. Just seek me out.
Okay, good. Thank you for the answers and questions from the audience, and thanks for the talk. Thank you, Víťa.
You're welcome.